All right. Okay, let's see. Getting people in here. Seeing anybody yet, but I'm getting them in. Haley, you there?
Yeah.
Okay. Jennifer. Okay, I see you. Jennifer, you there?
Yep.
Okay, good. Tori, you here? You there? Here, there, anywhere? Yeah. Okay. I got Stephanie. Are you in yet, Stephanie? I'm not sure about that. Bree.
I'm
Bree's
here.
okay, good. All right, good, Bree. Okay. Stephanie, did you get in? Trying to.
Yes, I'm here.
All right, good. Okay. So far we got Stephanie, Haley, Jennifer, Michelle is here, and Tori. Oh, people are bouncing around. What's going on here? I got bumped off this morning in my first class, so that means my internet's glitchy for some reason, but just I will bump myself completely off and then I will try to get back on if that happens. So just take a break and hang on. All right, guys, I'm gonna go ahead and share the screen while we're waiting for people. And then see if you got any questions. On the homework, I didn't quite finish what I wanted to do yesterday, but that's fine. We'll look at it again. Daggone it. Let's see. I think I'm still in. Let's see what we got here. Okay. All right. Good. All right. So while we're waiting, guys, I don't think I have anybody left in the waiting room. Guess not. Okay. While we're looking at this, let's just kind of glance over what we did yesterday, and then we'll move on a little bit. I have not gotten around to all the tests. I'm still trying to get some of the glitches worked out. Please send me your test in a PDF if you can. JPEGs don't transfer over to my grading system, which means I throw it from the computer onto the iPad and I can write on the iPad and send it back. And the JPEGs don't work on that. It's just the PDFs. I used to ask somebody, say, well, what's so special about a PDF? And now I know. I've learned a lot this semester. Probably learned a lot more than most people who were more familiar with the technology than me. But anyway, that's a good thing. When you're forced to learn, you learn. What happens? What we did yesterday was we talked about this exponential function, and basically we said one of the main. So I'm making you dizzy going back here. One of the main things we did with the exponential function. We had some applications of some of these things, and we figured out how to use the computer. And I'm still, even here towards the end, I think I might have gotten a TI-84 simulator downloaded onto my screen. If I have any extra minutes left with you guys today, I may try it out, which means I don't know if it'll come up or not. But it'll allow me to show you what I'm doing on the computer, and then on the calculator, and then you can do that. TI graciously has given a 6-month license to anybody who's teaching during this pandemic time, and they were good to their word. I got a license for 6 months, and here we go. I didn't realize I could do that. So okay. So one of the things we talked about was how this was dealt with compound interest, and we talked about the difference between simple interest and compound interest. Basically what we said was that when we're doing compound interest, we're getting interest on our interest. So as soon as they compound my interest, they throw that interest back in, and I start getting interest on that interest. And what we came up with was a formula that looked like that, where A was the amount you have, you'll accumulate. P is the amount you start with. R is the yearly rate. Make sure that is the yearly rate, and you put it in a decimal form. For instance, if we had 4%, we would have put in 0.04, not 4. If you put in 4, you mean 400%, and that's not going to happen. Okay, So the n is the number of times you compound it per year. So I'm sort of splitting this yearly rate into however many parts. If it were quarterly, it'd be 4, and so on. Again, the number of compoundings times the time in years will give you the total number of compounding. So if I had quarterly compounding for 10 years, 4 times 10 would be 40 compoundings here. So the formula is not too hard to use. It is an exponential formula. We're usually given R and N, and T is our variable. So when you graph this thing, I think I mentioned it yesterday, but when you graph this thing, it doesn't look like it's simple interest. It looks like an exponential function, which it goes up like that instead of going up linearly. And if you look at the linear part, that's simple interest. And the longer the time gets, the less time you're spending getting interest on interest if you're doing simple interest, because remember what they did was just give you the same amount every year and didn't add it back into the principal. So you get compound interest is this nice exponential curve. We did some problems with that. We said, well, you know, if it's good to compound it more times, why don't I compound it instead of quarterly, monthly, daily? Why don't I do it every minute? Why don't I do it every second? And what we found out from that was that if we let the n right here go to infinity, this thing goes to 0. And then it started to look like this definition of E right here, which meant that we had this formula that where this thing would reach a limit, okay? And where it reaches the limit, the best I can do was what we call continuous compounding, okay? So what I had asked you to do in the homework there were some problems where you did continuous compounding. You did compound, just regular compound interest where you're not doing continuous compounding. And you just found out what your values were and so forth. There was one thing I didn't get to, it was present value, but let me see if you're having any trouble on the homework. Is anybody having any problems on any of the homework here? Okay. There we go. One of the things we did in class was a table like this, where we started with our original amount, and I did this just for 1 year. You had a quiz that is going to look like this. I think that quiz is due tomorrow, and was filling in a table like this. And Haley, you're going to have to help me with this. Because you asked me this the other day. On that quiz, yesterday, on that quiz, I had left out the time in years on this table. Do you remember what I said I wanted you to let it be?
5 years.
Okay, 5 years. Okay, so in the problem that I gave you for a quiz, you just be using this was after 1 year. What I want you to do is change it in that problem to 5 years, but it's online. so print it off and finish the table. And then there were a few other problems on there that you were going to graph using your calculator and finding some values with E. Anybody have any question about any of that at this point? The one thing I didn't do yesterday that I wanted to do that was in the homework, and it's actually pretty easy, is present value. And in present value, what happens is that you figure out how much money you want at a period or a time in the future, and you say, if I'm given an interest rate and I want to leave it in a certain number of years, how much would I have to put in now to reach that value? That's called a present value. And actually, so in that kind of problem, we're given the amount that we want to reach, we're given the rate, we're given the time, and we want to find P. Well, actually, you could write a formula for that by isolating P. And you could isolate P by dividing by e to the RT. Okay, so P is A, E to the RT. Now, I will say that most books you won't see it like that. You'll see it where this is brought up into the numerator. And we know when we bring things up into the numerator, their signs change. So there's the formula for present value. given I have an amount in the future I want, I know a rate, I know a time, it'll tell me how much I need to put in right now to achieve that. So guys, look at this next one. Excuse me. How much would I have to invest now? So that's a P, I want to know P, to have $8,000 in my account in 10 years. So that's the amount I want to have in 10 years. Of course, that's my time. My interest rate is 5%. I'm going to tell you that I'm going to compound it continuously. I'm going to do the best I can. That's the best you can do, is compound continuously. And not to mention the fact that if I didn't compound continuously, you guys would have to, I'd have to subject you to suffering through logarithms to be able to solve what I need to solve. And that one, so we're just going to do continuous compounding in these problems. So here's what it looks like. If I were to just put everything in and not just use the formula, it would say, okay, 8,000 is what I want in the future. P is what I'm looking for. My interest rate is 5%. Again, do not put a 5 in there, put 0.05. Percent means per 100. So 5 over 100 is 0.05. And I'm willing to keep it in there for 10 years. So all I need to do is to solve for P. And all that entails is to take 8,000 and divide by E. Now, 10 times 0.05 is 0.5. So that'll make this problem a little easier here. Again, I just multiply those two things. Or you can put it in the calculator and let it multiply it. Find me a value for that, guys. I don't even think I have a value for that. Find me a value for 8,000 divided by 0.5, e to the 0.5. So e, remember, is second log. So I'm getting, put in 0.5. So somebody tell me what you got. Somebody give me an answer there after you put it in your calculator. Anybody?
4,852.
4,852.25. Give me my cents again, okay? You don't want to leave anything on the table, okay? 25 cents won't buy much, but it's 25 cents. Everybody okay with that? Everybody okay with using your calculator there? Again, the E is second ln, and then you put in your power, which is 0.5 in this case. So once again, what that is okay, if I want to have $8,000 10 years down the road, and I don't touch the money in the meantime, and it's getting 5% compounded continuously, I need to put in this right now. Now, I will say a word about this, and I'm not trying to pick on you, Stephanie, but if I left the 25 cents off, it wouldn't quite make 8,000. Okay, so you need that in there to make it actually work, to make it what you want. I mean, it might be 7,999.75 cents, but to make the 8,000, that's exactly what you need to. And because I had to round that a little bit to get to the nearest cent, it might even give me a little more than 8,000, but that's what it looks like. Okay, question, anybody about that? So I think that's all that I had from yesterday. I mean, yeah. So let me go back, and there's one more thing I want to do with these exponential functions. I really haven't talked about their derivatives. And the derivatives, I want to give you the derivatives because the derivatives aren't that hard, and we can do all the same things we normally do. We can do rates of change. We can do slopes of tangent lines to curves with this new function. If I know what the derivative is, we can find out where one of these functions is increasing or decreasing. Okay, so I'm going to start to look at section 4.3. So the question is, what's the derivative of e to the x? Couple of things I want you to recall, and I'm going to run through a little bit of theory here, so you just watch me and sort of see where I'm going with this. We found out, even by looking at the graph and by the definition in the book, and we used it actually to do the interest problem, that E was the limit as x approaches 0 of this thing right here. And one of the things we did was graph that And we saw it looked kind of like, this. And as we approach 0, this approached that number 2.71 that we know as E. Okay. Now I'm going to make a little switch here, and you'll see why I'm doing it in just a second. It doesn't matter what you're letting go to 0. If I replace that, if I put X here, there's an X there, there's an X there. If I put delta X here, and there's a delta X there and a delta X there, it's still going to go to E. I mean, it's called a dummy variable, really, guys. If I let it be T, the limit as T goes to 0 of 1 plus T to the 1 over T is also E. Now, what that says is that as I get closer and closer to 0, in other words, for small values of delta X, E is approximately this thing right here. It gets closer and closer to it. If delta X is really tiny, if I'm coming really, really close to 0 right here, I'm getting really, really close to E. So we'll just say it's approximately E. Now, you might wonder why I'm looking at this delta X, but I'm gonna do a couple more things with it, and I think you'll see. I know this. Now, what I'm gonna do is raise both sides here and here to the delta X power. So that'll be E to the delta X. And if I raise this one to the delta X, I'll get that. So that'll be a delta X there and a delta X there. I'm raising it to that power. Now, what that does for me is something I'm going to need in a second. Notice what happens when you raise a power to a power here. I mean, what do you get when you do, you multiply them? That's my property of exponents. Like x cubed squared is x to the 6th. You multiply them. So 1 over delta X times delta X is just 1. So what that says here is that E to the delta X is this thing right here. Now again, the notation is kind of messy, guys, but I hadn't done a whole lot different. I used this definition. I replaced the X with a delta X. I raised both sides of that thing to the delta X, and I get this thing right here. Now, here's why I wanted to change it to delta X. And this is going to throw us way back. It seems like 50 years to me right now. I want to find the derivative of this function. And this function that I'm looking at now is f of x equal e to the x. When we first started learning how to take derivatives, we had this limit definition of derivative. After that, we got some rules like the power rule. We didn't have to go through this. If you remember, you would plug in x plus delta x, and you would subtract, you divide by delta x, you take the limit as x goes to 0, and you would find the derivative. All our power rules are derived from this, and we now just use the power rule. We don't use the definition every time, okay? But we can't use a power rule on e to the x. It's a very different kind of function. It's not x to a power. It's actually a constant base to a variable power. And you might say, well, why can't we just bring down x, e, and take away -1 to get the derivative? And the reason is that's not true. It doesn't work for that. So for instance, if I had f of x equal x squared, where I have a variable base and a constant power, that's what I can use the power rule on. That's all that I can use the power rule on, x to some constant, so 2x. So I'll give you another example. If I had x to the e, well, e is just a number. F prime of x would be e x to the e minus 1. I just take away 1 from it, but that's not what I have. What I have is this exponential function here, e to the x. So here's what I'm going to do to take that derivative. It will not work with a power rule, so don't even try to apply the power rule to it. It will not work. I'm going to take this function, and I'm going to find that function evaluated at x plus delta x. Now remember what that means. That means in the function, just put x plus delta x in the place of x. So that's what I did right here. X plus delta x in the place of x, and then minus e to the x over delta x. Now, let's see if we can find this limit. if I break this down, remember I've got a common base here of e, and when we have like bases, we add powers. So I'm going to do something backwards here. We're used to putting the two together. Now I'm going to break them apart. So e to the x times e to the delta x is e to the x plus delta x. So I'm breaking them down. The reason I did that was because I could pull out an e to the x. Okay? And the reason I did that is because I think I know what this one looks like. E to the delta x minus 1 up here, look at this. We had e to the delta x was 1 plus delta x. So what I actually need is e to the delta x minus 1 here. If I take 1 away from both sides, I'll have delta x equal e to the delta x minus 1. Now again, I'm going through the theory, but that's easy to see. I mean, I can just solve for it. That's that. What happens now, I replace that. There was a minus 1 there, and I replaced it with the e to the x minus 1 right here, which was 1 plus delta x. The 1's go. I then just have a delta x over delta x, which is 1, and I end up taking the limit as delta x goes to 0 of e to the x. Well, e to the x, all the delta x's canceled out here, guys. They gave me something 1. So I don't have any delta x's. This is like taking the limit of a constant. It doesn't have any delta x's in it. And the limit of a constant is that constant. Now, I just applied the limit definition of derivative to e to the x. And again, that's all the theory there. But I just applied it to e to the x, and I came out that with its derivative was e to the x. That's nice. Here is a function, unlike any other function we're going to see, that is its own derivative. It's its own derivative. So right here is where I've said that. If f of x is e to the x, then f prime of x is e to the x. It's its own derivative. Can't get much easier than that. I'm going to change it up a little bit in a minute, but it's its own derivative. So let's look at a couple of examples. If I said to you, let's let f of x be 5e to the x. Now, we know the derivative of a constant times a function is just the constant times the derivative of the function. You might say, well, let's use the product rule on that, but you don't have to do that. It would just say 5 times the derivative of e to the x, which would be just e to the x, plus e to the x times the derivative of 5, which is 0, so you don't have to do that. The derivative of a constant times a function is you just repeat the constant and then take the derivative of the function. It's like, if you remember, guys, if I had f of x was 4x cubed, you're used to telling me very easily now that the derivative of that's 12x squared, but if you left the 4 there and then just took that, you would see that it's just the 4 times the derivative of what's there. And then you could multiply the 4 times 3 and get 12. We don't go to that trouble anymore. We just go ahead and multiply it all in one whack, okay? But the derivative of a constant times a function is that constant times the derivative of the function. So that's nice. The derivative of 5e to the x is 5e to the x. If I look at f of x equal e to the x over 2, if you look at that, it's just 1/2 e to the x. So the derivative of 1/2 e to the x, for the same reason that it happened with 5, is just 1/2 times the derivative of e to the x. But e to the x is its own derivative. So you get 1/2 e to the x. Okay? Now, let's use some of the other things that we know to do some other problems. Basically, the bottom line here, guys, is if this is an e to the x and that's a constant, it's just going to be, you're going to get the same thing back. All right, you're going to get the same thing back because you're going to repeat the constant and the derivative of e to the x is itself. Question about that, anybody? So it's a new function. We're trying to find its derivative. We found out something nice about it. It is its own derivative. All right, let's go to another problem. All right, I want us to look at this one right here. Now, guys, it does have an e to the x in it, but that e to the x is multiplied by some other function. Tell me what rule you're going to use on this. What rule, and we're going to remind ourselves of all these rules right here at the end. What rule am I going to use when I have one function times another function? I'm listening. One function times another function. We hadn't done it in a while.
Product.
Yeah, the product rule. And the product rule said the first times the derivative of the second plus the second times the derivative of the first. So I'm going to write that down so we remember it. First times the derivative of the second plus second times the derivative of the first. That, guys, is the product rule. So when I use it on this function, I'm going to let that be the first one and this be the second one. So it's going to be x squared. That's the first. The derivative of e to the x is itself, e to the x. Plus the second is e to the x. What's the derivative of x squared? Right there. What's the derivative of x squared? It's just, that's an easy one. It's just 2x, right? Yeah. So we would, if I write it a little nicer, I'd have x squared e to the x plus 2x e to the x. Now, because of something I'm going to do in a few minutes, I want to point out something here, guys. Since e kind of repeats itself because it's its own derivative, when you get to the end of a derivative like this, there's almost always something that'll factor out. And because e to the x is repeating itself, notice it ended up in every term here. So I could factor out an e to the x from this. Do you see anything else I could factor out from this? From these, look at this one and look at this one. What do I have in common between the first one and the second one?
An x.
You got an x and you got an e to the x. I'm going to do that. I'm going to pull out an x, an e to the x, and what will I be left with, guys? Pulled one x out here and the e to the x. What am I left with there?
You're left with an x.
Yeah, I'm left with an x because I pulled out one and I pulled out the e to the x. I'm left with an x. And I pulled out an x here and I pulled out the e to the x. What am I left with out of that one?
2.
Just a 2. Now, I'm going to say something right here that's going to remind you of some other words I've used a lot over the semester. What if I said to you, I want you to find the critical numbers of this thing? Remember, critical numbers are where the derivative is equal to 0 or fails to exist, and it exists everywhere here. So the question would be, where would this be equal to 0? In other words, what are the critical numbers? Let me say one thing about e to the x. Let's recall when we looked at the graph of e to the x, it looked like this. And it was always positive. It never crossed down below into this negative section here. And when you see an e to the x or an e to the minus x, e to the minus x looked like that. It went the other direction, but it still didn't go down into negative territory here. E to the x is positive. So that's never going to be 0 right there. What would make x plus 2 0? Anybody? What would make x plus 2 0?
-2.
All right. So x equal -2 is one of the critical numbers here. What would make x 0? In other words, when is x 0?
0.
When x is 0, okay? So there are 2 critical numbers in that, 0 and -2.
So you don't do anything with the e to the x?
No, because it's always positive. It never is 0. It never is 0. Because you remember what the graph looked like? It never went down into this territory down here. And even if you looked at e to the -10, it would be 1 over e to the 10th. It would be a very, very small positive number, but it would still be positive. Okay? So I can do some of the same things I've been doing before with this new function. I can find critical numbers, but that's one thing you're going to remember. This e to the x part, never zero. We'll look at that a little later today. All right, let's look at another example of a derivative. What rule do you think you're going to use to do this one right here? Anybody?
Quotient rule?
Yeah, quotient rule. It is a quotient, guys. Bottom, remember what that said. Fortunately, the last half of the semester has been open book, open notes. So if you don't remember the quotient, you got to remember that you got to use it. If you don't remember it, you can just go back and look at it. It's the bottom, low, d high, the derivative of the top. And the derivative of the top is just 3 e to the x, because e to the x is its own derivative, minus the top times the derivative of the bottom. What's the derivative of the bottom here, guys? That one's an easy one. What's the derivative of the bottom? Anybody? What's the derivative of 1 plus x cubed?
3x squared?
3x squared. Yeah, derivative of 1 is 0. Derivative of x cubed is 3x squared. So there's 3x squared. And then we wind up by squaring the bottom. I'm not going to simplify that one, but it's bottom times the root of the top minus top times the root of the bottom over the bottom squared. So we just got this new function, and we can work it into all our old rules just like it was any other function. All right, I'm going to try another one here. What's the derivative of this one? Now, one thing we know about derivatives is if they're added and subtracted, if they're functions that are added or subtracted, we can walk down the line and take derivatives of each of them. So the derivative of 4e to the x is 4e to the x, because e to the x is its own derivative. And the derivative of x cubed is what, guys?
Minus 3x squared.
Mm-hmm. What's the derivative of 3x?
3.
3. So there it is, the derivative of that function that had an e to the x in it. Okay. All right. Everybody okay with that? I can kind of see some people, but I can't see everybody because not everybody's camera is working. Okay. I'll try another one here. The next one, I just put it in here to remind you of something, guys. Based on what we said a minute ago, that's two functions multiplied by each other. I'm going to use the product rule on that. But what I wanted to remind you of was that you need to rewrite the square root of x. So before I do anything here, I'm going to rewrite that as 2x to the 1/2. Okay, now this, as I said, everything at the beginning of the semester seems a million years away, but it's just another product rule, and we had to rewrite things. So it's going to be a product rule, and the derivative, I'm going to run out of space down here, but the derivative is going to be the first times the derivative of the second, but e to the x is its own derivative. Bingo. I don't have to worry too much about that. Plus the second times the derivative of the first. Now there's the first right there. So if I bring down the 1/2, I'll have a half gone. I was simplifying in my head there. I was not going to, I have a 2 already there, so it's a half times 2 x to the, if I take away 1 from a half, I get minus a half. I can do a little simplification on that, guys. The 2's will certainly cancel out there. We'll wind up with that. Now, here's another one. Last in the set. What's the derivative of e cubed? What's the derivative of e cubed with respect to x?
Would it be e cubed?
Well, let me ask you, is there an x in that function?
No.
Then if there's no x in it, what's it commonly known as? There's no variable in there either, guys. E, remember, E is 2.71. And that's just a number. What's the derivative of a constant?
Should just be E.
No. What's the derivative of any constant? If I
Oh.
said f of x is 6, guys, what would the derivative of 6 be?
0.
It's 0. Everybody agree with that?
The derivative would be 0.
So the derivative of this thing is just a number. It's an ugly number. It's got this e that represents what it is, but it's the derivative of that one is just going to be 0. I don't know if I did this to you guys or not. I always do it to my Math 100 class. A lot of times I'll say to them, what's the derivative of pi squared? And they'll always tell me, well, it's 2 pi to the first. Well, no, it's not. It doesn't have an x in it, guys. Pi is about 3.14. 3.14 squared is 9 point something. What's the derivative of 9? It's just 0. Okay, so those things don't have x's in them. They're constants, and their derivative is 0. Okay, so we can do some of the same things with this derivative that we did before. We can find the slope of a tangent line to the graph of something. So for example, if I graphed 2e to the x, and notice what I did here. I just plotted a few points. If I let x be 0, 2e to the 0 would be 2. So there's that point right there. So it's 0, 2. If I put in 1, 2e to the first is about 5.4. I can find that using the calculator. So right there at 1, I get 5.4 for my point. If I put in -1, I'd get 2e to the -1. You put it in the calculator, it's about 0.74. Guys, this little squiggly right here over the equal sign means approximately. I'm having to cut this thing off because it's an irrational number, so I'm just going to take it to a couple of places, just enough places to see where it gets graphed here. So down there at -1, it's 0.74. We know what the exponential function looks like. It should, when you put your points on things, it should look like that. This is very similar to one of the problems I gave you on the quiz that's due tomorrow. Just make your table, and I actually put out the table with the values there. Tell me what your values are, put them on the graph and graph it. Now, what did the derivative tell me? Well, I'm going to say, I know that the derivative of this thing is just 2 e to the x. 2, I forgot my e to the x. Because it's its own derivative. So if I said to you, I want to know what the slope of the tangent line to the curve is at 0, find the slope of the tangent line of the graph at x equals 0, I would put a point right here at 0 and I'd say, okay, there's the tangent line. Let's find its slope. On your final, I'm going to ask you a question. I'm going to say, what's the derivative? And you might give me the limit definition of derivative. You might say it's the slope of a tangent line to a curve at a point. You might say it's the rate of change of a function. It's a derivative is a place where you can find horizontal tangent lines or the increasing, decreasing. There are all kinds of things you can do, okay? So that's one of the things we could do with the derivative. So what we know then is that the slope here at 0 is f prime of 0. And that's going to be 2e to the 0, which is equal to 2. So the slope of that line right there is 2. It goes through the point 0, 2. Again, the slope of a tangent line to the curve is just that point, x point, plugged into the derivative. Once I ask you what that is, I might say, well, what's the equation of the line? Well, there's a point right there. There's the slope. Y minus the y coordinate is the slope times x minus the x coordinate, and there's my line. I can play it out. That'll be y minus 2 is 2x, which means y is 2x plus 2. Okay? So we can do a lot of the same things. We can do all the things. We just got a new function to do with it. Okay, I got one more rule for you. And we'll practice some on that and then maybe look at a couple more examples. This will be the last new derivative you get for this course. This is it. This course is about a lot about derivatives. We may do a few things called anti-derivatives, but this is all the derivatives. I got another rule that that I need to use often, and that rule says if f of x is e to the g of x, then f prime of x is e to the g of x times g prime of x. Guys, what I'm saying here is that there's not just an x there, it's some function of x. This is a result of something called the chain rule. And essentially, you've got a chain of things you're interested in. You're interested in the e part of it, and you're interested in the fact that you're raising it to a function of x now, not just an x. So let's look at this one right here. This is in this form, because this is not just an e to the x. Now, I did say to you the derivative of e to the x is e to the x. So this ain't e to the x. This is e to the x squared. So we know that the 5 is just going to sit there. What this rule says is that, in a way, it behaves like e to the x. It does repeat itself. But because this is a function of x and not just an x, I must multiply by its derivative. Well, what's the derivative of x squared? Anybody?
2x.
2x. And if you multiply out, that'll be 10x e to the x squared. Okay? So if it's e to a function of x, not just x, and actually it works, you can, if you want to remember this rule, you can remember it for this one too. If we say it's its own derivative, that's true because it's e to the x, and the derivative of x is 1. See, if I take the derivative of the power, I get 1 there, so I just get e to the x back. That's the only case where I get the actual function back. All right, let's look at this one. Notice, again, e to a function of x, not just e to the x. It repeats itself. And then it follows it, in parentheses, please, by the derivative of the power. We've done a lot of derivatives of polynomials here. We did a whole bunch on the last test. That's going to be 3x squared minus 3.
So you basically just repeat the function, then you multiply by the derivative of the power of the function.
That's exactly it. You repeat it. It is, in a sense, the derivative of itself, but you got to compensate more because it's not just an x here. You multiply by that. That's a kind of lame reason for this, but I don't have time to talk to you about.
And then you solve it like you finished.
Yeah, you could do. Let's see what we could do with this. You might say, well, this is e to the x squared minus 3x plus 1. And that's never going to be 0. I could pull, let me go down here. I could pull a 3 out of this one, and I'd be left with x squared minus 1. So it would actually look like e to the x squared minus 3x plus 1 times 3. And if I factored this, it would be x minus 1 times x plus 1. E to anything is never going to be 0, guys. 3 is never going to be 0. What would cause this derivative to be 0? What's the only values of x that would cause this derivative to be 0?
-1 and +1.
Right, -1 and +1, because those are the only things that could become 0. So we would say the critical numbers here were x equal 1 and x equal -1. E to anything is always positive. It's never gonna be 0. So I'm gonna write it right here, never 0. All right, never 0. Okay, we'll do one more. What rule am I gonna use on this one, guys? 2x squared plus 1 times e to the 5x. You hear yourself saying times, what rule are you going to use on this thing? What is it? When I say something times something else, it's what?
Product.
It's a product. I'm gonna use the product rule. This is a good review for stuff we're gonna have to remember. First, times the derivative of the second, it repeats itself, then multiplies by the derivative of its power, which is 5, plus the second times the derivative of the first, which in this case is 4x. Guys, I use the product rule on that. Please do not just do this one and do that one. That's wrong. Only if you got a string of things added and subtracted can you do that. You can't just do this one and do that one. If it's a product, you've got to use the product rule. This is a good review here with a new function. Ooh, this is bad. You know what? It's so bad that I'm not going to do it. Can't read it. I'm not going to do it. That's a sign, because I was a little bit hesitant about that one anyway. Let's try another one. Let's do another one. It's a little fuzzy too, but I'm going to do this one. All right. So we spent a major amount of time analyzing graphs. And what we did first was take the derivative. And this one is going to be a product rule. For e to the x, or x times the derivative of e to the x, which is e to the x, plus e to the x times the derivative of x, and that's e to the x times 1. So what I get here, that's blurry, guys, but it's x e to the x plus e to the x times 1. Now, let me point out something. When we were analyzing a graph, the very first thing we did was find the derivative, and the second thing we did was find the critical numbers. And I already kind of hinted at this a little earlier today. I'm going to pull out the e to the x. It's in both terms. It tends to repeat itself. So when I pull it out, I'm left with an x, and I'm left with a 1. E to the x is never 0. So what's the only way this derivative can be 0? What's the only way this derivative can be 0?
If x equals -1?
Yes, if x is -1. That's what will make that 0. So I'm gonna put a -1 on the increasing decreasing line, because that's what I'm finding with the first derivative, increasing decreasing. So I'm going to test it. This was not hard to test, but I'll pick a number over here. Pick 5. 5 plus 1 right here is going to be positive. E to the x is always positive. I don't have to find out what e to the 5 is. E to the x is always positive. So this is a positive times a positive. That means this thing over here is increasing. If I plug in something less than -1, say -2, it will make this negative. E to the x is always positive. So a positive times a negative is going to be negative. That means I've got decreasing. Now, can you tell me what's going on at -1? What else can you tell from this increasing, decreasing graph, guys?
A local min.
Yeah, it's a local min. Good. It's a local min because you got coming down, you got going up. So what we say is that there's a local min at x equal -1. It is f of -1. Now I got to go back to the function here. That'll be e to the -1 times -1, and you do need your calculator to find that because we don't know what e to the -1 is, but I'm going to find out right now. I'm going to go second log. I'm going to put in a -1, and then I'm going to multiply by -1. Check it out. It'll be -0.37, about -0.37. So there's a point on that graph where there's a low point, and it looks like that. All right, finally, I'll finish up here, guys. The second derivative tells me about concavity. Here was the first derivative. I'm going to remind you of that. How do you take a derivative? You take a second derivative by taking the derivative of the first derivative. It's also going to be a product rule. So first times the derivative of x plus 1, which is just 1, plus the second X plus 1 times the derivative of the first. Derivative of e to the x is e to the x. Notice that the e to the x appeared in both. I'm going to pull out the e to the x. I'll be left with a 1 and an x plus 1, which is an e to the x times x plus 2. Now, for the concavity, we're going to put the 0 on that graph. What's the only thing that's going to make that 0 right there, guys?
-2.
-2. To the right of -2, say it's 0. This will be positive. That's always positive. Positive, that means concave up. Right here, to the left of -2, say at -3, that'll be negative. That'll be positive. That's going to be negative, so that's concave down. There's an inflection point at -2. Go back to the original function. See, I don't even remember what it was. X e to the x. It would be -2 e to the -2. Give me a quick second to evaluate that. That'll be -2. That's going to be a small number there, guys. This is going to be a graph. Let's see, let me find it. -2 times e to the -2. -0.27. Now, these are small numbers there. But here's what I want you to do, and we'll pick this back up tomorrow. I want you to put this on the calculator. I want you to do f of x equal x e to the x on the calculator. And by tomorrow, I'm going to see if I can show it to you on the calculator. But I need to practice with this thing on some other guinea pigs. And put those problems on there. Make it these are very small things. Here's my suggestion on the calculator. I want you to put the window from on x from -4 to 4. And on y, I want you to put it from -1 to 1. And see if you see an inflection point. See if you see the local max or the local min. Put it on there and we'll match it with what we've got right there, okay? So try that for tomorrow. Don't forget you got that quiz on the compound interest stuff tomorrow. So I did not get to your test last night, as I said earlier. I've got to get to them because I'm getting stacked up here. There's lots of trains waiting to get into the station here. But I will do my best to get that back as soon as possible, okay? Definitely by the end of the week. Try that. We'll talk tomorrow about this again, and I'll see you tomorrow. Anybody questions or anything? Okay, I'll see you tomorrow.
Thank you.
Bye-bye.
Bye.